Okay, everyone, can you all take your seats? So our next session chair is David Held from Carnegie Mellon University.
Hi, everyone. Just a reminder, please try to take your seats quickly and quietly since the next session is starting now. The first paper that will be presented is Equivariant Transporter Network, presented by Haoji.
Hello everyone, I'm Haoji from Northeastern University. Today I will present our work Equivariant Transport Net that is built on top of the baseline transport network but could achieve more sample efficiency. This work is collaborated with Gen Wang, Robin Waters, and Robert Plant. Here is the manipulation pick and place task. After picking the orange object, the bot needs to place it inside the green outline. If there is a rotation of the picked object, the place action defined as the relative pose between pick and place should change accordingly, but could learn the pick and place knowledge from left configuration be generalized automatically to right configuration. And interestingly, we found the design of transport net could satisfy this equivariance. We refer it as CN equivariance. But what if there is another rotation on the placement? Could learn the pick and place knowledge be generalized as well? And our model is designed to satisfy this CN times CN equivariance. Let's first go through the architecture of transport net. Given the observation OT, typically a depth image, the pick module will first output a proper pick location, then a stack of different rotated image patches around the pick is sent to a sign network. We refer the operation of rotating the image n times as the lift operator denoted by R sub n. The output of the sign network is cross-correlated with the dense feature maps from the observation to output the place features, where the place angle is discretized and defined on the channel axis. So if there is a rotation on the picked object, the output of the sign network will undergo through permutation due to the lift operator. And after cross-correlation, the best channel of the place features will also permute, which is reflected as the change of the best place angle. It indicates the learned place knowledge could be generalized to rotations on the picked object. But the transport net cannot generalize the learned knowledge to rotations on the placement. How could we add the second type of equivariance to our model? The operation is simple. We explicitly encode both the fin network and the sign network as CN equivariant models. We also make our pick network equivariant, as highlighted in green. Specifically, rotations on the input are equivariant to rotations on the output. Due to the equivariance of both fin and sign, cross-correlation became an equivariant operator. It means rotations on the placement can be transformed to the no-rotate image equivariantly. By combining the two types of CN equivariance together, our model could achieve CN times CN equivariance. It could generalize the learned pick and place knowledge through rotations on the picked object under the placement. Together with the transitional equivariance of CN, it covers the most symmetries of 2D pose. We first evaluated the performance of our model on Reference 10 benchmarks that covers various manipulation, pick and place tasks with a suction gripper and UR5 robot. Table 1 shows the performance of our model trained with a different number of demonstrations. So firstly, our model could outperform the baseline transport net on our tasks. And secondly, with less than 10 demonstrations, our model could achieve greater than 95 success rate on 7 tasks. Thirdly, with either 1 or 10 demonstrations, the performance of our model is better than the baseline trained with the standard demonstrations on 5 tasks. So it indicates the sample efficiency of our model. Then we select 5 tasks from round 10 and replace the suction gripper with pedal jack gripper. This requires additional picking angle inference. Again, our model could outperform the baseline in terms of the sample efficiency. So based on the sample efficiency, we could collect 10 human demonstrations on a real robot and then train a model. So there is no symmetry real gap. Table 3 shows the results for 20 rounds after 3 tasks. Learned policy is near optimal in terms of the success rate. Yeah, that's it. Thanks.
Thanks. So the next paper will be RoboCraft, presented by Hao Chen.
Hi, my name is Hao Chen Shi. I'm a first-year master's student at Stanford University. Today, I'm presenting our recent work, RoboCraft, learning to see, simulate, and shape elasto-plastic objects with graph neural network. This is a joint work by Hua Zhe and Jia Jun from Stanford, Zhi Ao from UC San Diego, and Yun Zhu from MIT. Our task for the robot is to use a parallel 2-finger gripper to deform an elasto-plastic object into a target shape, such as the letter X on the top right corner. Our result of shaping X is shown at the bottom right corner. It's very challenging to shape an elasto-plastic object into a target shape from perceptive RGBD data. There are many important questions to answer. For example, how to work with noisy and sometimes occluded RGBD images, how to predict the motion of the elasto-plastic objects, which has very complex dynamics, and how to plan a good solution in a very large action space. To address these challenges, we propose RoboCraft, which has a complete pipeline of perception, dynamics, and planning. As an overview, perception constructs a particle-based scene representation from raw RGBD data. Dynamics predict the motion of an elasto-plastic object with a graph neural network. Planning figures out optimal control solutions with sampling and gradient-based trajectory optimization. We will walk through them one by one. In the perception module, we first extract the plastic point cloud from the scene, then reconstruct a watertight mesh around the point cloud, and lastly, sample a sparse point cloud inside the mesh. Then we will have desirable inputs to our graph neural network. However, an important issue comes up. Since the particles at each time frame are generated from sampling, they are unordered, and there's no temporal particle-to-particle correspondence between them. So this makes L1 or L2 loss used in previous works not applicable. So we use 3D distribution loss, such as transfer distance and Earth mover's distance as a training loss. Then we use a graph neural network to learn the dynamics and predict how the particles will move when applying an action. We demonstrate in our work that only 10 minutes of real-world interaction data is needed to learn the complex dynamics very well. With the trained dynamics model in hand, we use sampling and gradient-based trajectory optimization to find a robot trajectory that leads to the most similar shape to our target shape. In the real world, we collect data by first resetting the plasticine with a mode and then randomly applying gripping actions to deform the plasticine. Because of the strong inductive bias introduced by the graph neural network, we only need 10 minutes of real-world interaction data to learn the complex dynamics sufficiently well. Here's the manipulation result of letter X in the real world. RoboCraft accurately predicts how the plasticine will move and leverage the gradient information to plan a trajectory with horizontal pinches and vertical pinches. Here's a more challenging task, manipulating a letter A in the real world. Although the shape of A doesn't seem very complicated, it's actually hard for me to quickly come up with a way to shape it. And RoboCraft figures out a creative solution that differs from what I had in my mind, but nicely completes the task. To demonstrate the difficulties of the task we are solving, we invite human subjects to complete the task with the same robot gripper. We show the results of them shaping C and Z in a simulator, and also their results of shaping R and A in the real world. Empirical evidence suggests that the proposed tasks are hard for both manipulation algorithms and human subjects. But RoboCraft is able to achieve comparable or better performance than humans when humans attempt to solve the task with the same robot gripper. You can find more information on the project website, and also feel free to contact me via email if you have any questions. Also come and check out our poster session. Thanks everyone for the attention.
Thank you. The next paper will be Play by Ear, presented by Max and Olivia.
We present Play by Ear, learning skills amidst occlusion through audio-visual imitation learning. Now, many real-world tasks require fusion and reasoning across multiple modalities. For example, if you're extracting keys from a bag, you need vision to perceive the opening of the bag, but you also need audio or touch in order to find the keys in the bag. And we're wondering if our robots can learn to do a similar thing. Now, it is true that many prior works have looked at fusing tactile information with visual information, but it is also true that tactile sensors can be expensive and brittle, and we're wondering if audio can provide a cheap and robust alternative in certain cases. Concretely, we mount a cheap microphone to the gripper of a robot arm, then we learn an end-to-end policy using vision and audio, and then we try to tackle heavily occluded tasks like extracting keys from a bag.
Our model encodes a spectrogram of the last 2 seconds of audio with a 1D convolution. It also encodes frame-stacked visual observations with a ResNet and concatenates the embeddings together with proprioception for a single time-step observation. Additionally, because an observation, like sound made when contacting the keys, can influence actions many time steps in the future when audio is not present, we consider the last 10 time steps when we produce actions. We train our policy end-to-end with behavior cloning on pre-collected demonstrations, then we fine-tune with online interactive imitation learning using human-gated Dagger. In our experiments, we consider 4 main questions. First, can our approach use sound to perform visually occluded tasks on a robot? Second, can our model generalize to unseen objects? Third, can our method use sounds to differentiate between objects? And finally, how does our approach compare to ablations and baselines in simulation?
For our first experiment, we consider the task of removing a keychain from a paper bag in which the robot cannot see inside the paper bag, meaning that it is a fully occluded task. There are 2 versions of this particular task. There's an easy version in which the keys make a sound immediately upon the robot reaching in the bag, and there's also a harder version in which it requires a sort of searching motion before any sounds of the keys are heard, which allow it to be localized and extracted. Our method completes the easy and hard versions of the task with 70% and 50% accuracy respectively. Now, without audio, our method fails because it cannot localize the keys in the bag. Without memory, our method fails because it cannot use past sounds to inform current actions. And interestingly, without vision, our method performs 20% worse because it cannot see the bag being deformed by the robot arm and therefore can get confused by the sounds of the crinkling made by the paper bag. So as can be seen here, again, that audio is critical for the grasping process. With the easier mode, we see that it makes sound upon reaching in, which allows for a quick and efficient extraction. Now, with the harder mode, we see that it does require this sort of searching action before any sound is heard, before it can be extracted. Now, in our next experiment, we wanted to see if that particular model can generalize to unseen objects. And we see that it actually indeed does for objects that make sounds upon contact, for example, a bag of chips. But it does not work for things that are softer and does not make sound, like a cloth. And this goes to show, yet again, that sound is critical in the grasping process. But it raises a larger question, which is, can we differentiate between the noises of different objects?
We test exactly that in our next experiment. The robot must grasp the bag, but only if it contains screws and not packing peanuts. To do so, the robot probes the noise of the bag by dropping it on the table and decides whether or not to go down and re-grasp it. Our model lifts the bag and then drops it. If it hears the sound of the screws, then it will go back down again. It is successful 70% of the time. Finally, we compare the ablations and baselines in simulation on occluded grasp and pick-and-place tasks. In Majoko, we approximate sound using external contact forces on the object. First, from the solid magenta line, we see that fine-tuning with interactive imitation boosts success rate over offline behavior cloning by around 20%. Second, from the dotted lines, we see that by removing audio, vision, or memory, the performance suffers like on the real robot. And finally, from the solid blue line, we see that fine-tuning via reinforcement learning instead of interactive imitation is much less effective. The key takeaways from our project are as follows. First, audio signals can be a cheap and robust alternative to tactile sensing in certain applications. Second, our method can accomplish manipulation tasks with heavy occlusion using audio, vision, and memory. And finally, our method can use sound to distinguish objects and change its actions accordingly. For more information, please see our project website and also our open source code. Thank you very much for your attention.
Thank you. The next paper will be the surprising effectiveness of representation learning for visual imitation, presented by Joe.
Hi, I'm Joe, and this is our work on visual imitation done with Mahi, Sridhar, and advisor Laurel. Our task is, how do we take a few visual demonstrations of a human doing a task, in our case, opening doors and cabinets, and have a robot, like the one shown on the right, be able to solve the same task. So here you can see our robot, which is the Hello Stretch, successfully opening the cabinet, which I collected demonstrations on in the previous slide. So typically, to do imitation or visual imitation, one would use behavior cloning. And behavior cloning, what you do normally is learn an end-to-end model, where the model takes in the observation, which is the robot's camera input, and an action, which in our case is a translation vector. However, because we want to use a few demonstrations, behavior cloning models are not ideal because they do well when you have a large amount of data. And in addition to large amounts of data, they can also require complicated priors or even complicated architectures to do well. So in our work, we wanted to simplify things down and propose a new model. So our model can be broken up into two key components. First is a representation model, which is just an encoder that maps images to representations. And this is trained through self-supervision. Then, with this encoder, we freeze it and do simple nearest neighbor matching. And this is how we calculate our action. So to talk in more detail about our model, the training phase is solely learning this encoder on our data set. So specifically, we use BYOL to learn our encoder. Now, once we have our encoder, we freeze it. And on test time, the robot sees an image. We pass it through the encoder. Then we do nearest neighbor matches on the representations and then aggregate those corresponding actions and weight them by the nearest neighbor distance. This is also known as locally weighted regression to computer action. So to talk more about the demonstrations, we collect in total 71 demonstrations opening various cabinets across various kitchens. We use the Reacher Grabber assistive tool with the GoPro mounted on the top. And on the right, you can see how the GoPro looks at the scene. The end effector is similar to that of the robots to minimize the visual mismatch. And we use structure for motion to extract actions from the sequence of images. So let's run through one full iteration of our algorithm. First, the robot takes an image through its camera, and notice that the end effector does look similar to that of the previous slide. Then we pass it through our encoder. Then we find the nearest neighbors in our demonstration set, take their corresponding actions, sum them but weight them by the nearest neighbors, the representation's distance, apply that action on the robot, so the robot takes a step, and we have a closed loop model, so the whole process starts all over again, and the robot takes another image. So here on the bottom right inset box, you can see what the robot sees in real time, as well as the red arrows, the action it's applying. So far you've seen the robot only open this specific cabinet. However, we do test on a variety of cabinets in our lab's kitchen. So here you can see our robot successfully opening another cabinet. And it's important to note that all these cabinets are present in our demonstration set. So on the variety of cabinets that we test on that are present in the demonstration set, our model does pretty well and achieves a high success rate. However, this naturally leads to the question, what happens when the model sees something that is not present exactly in the demonstration set? So to test this, what we do is add visual distracting features or occlusions to the cabinets, such as taping the key features like signs, covering the handle with tape, or even putting paper over like a prominent hole. And despite these moderate levels of occlusion, our model is rather robust and is able to open the door. However, when we push it too hard and cover too many key features, we do see our model is failing. And this is probably because there's no key features to do good nearest neighbor matching. But again, on reasonable amounts of modification, our model does perform reasonably well. In addition, we also test our model on 2 offline tasks, namely stacking and pushing. So for the query column, you can see the nearest neighbors are matching across different objects and environments. And we also want to see, is it the representation or the nearest neighbor that contributes most to our model success? And we find that both are equally important to achieve our results. If you want to look at the code, data, or even read the paper, please check out our website. Thank you for listening.
Thank you. The final paper of this session will be Mesh-Based Dynamics and Occlusion Reasoning for Cloth Manipulation, presented by Zishuan.
Good morning, everyone. My name is Zishuan from Carnegie Mellon University. Today, I'm going to present mesh-based dynamics with occlusion reasoning for cloth manipulation, which is done in collaboration with Xinyu Lin and David Held. Suppose the robot wants to unfold this shirt. One of the greatest challenges is the occlusion. Due to the partial observability, we can only directly obtain the state of the visible cloth, while the occluded regions remain unknown. Understanding and inferring the structure of the occluded regions is important for tasks like cloth unfolding. However, it remains unclear how to estimate the occluded regions effectively for arbitrary cloth configurations. One possible way for inferring the occluded regions is explicit reconstruction by using a neural network. However, this is extremely challenging even for the best neural network due to the deformability and high dimensionality of the cloth, as well as the ambiguity caused by occlusion. Prior works try to simplify this challenging issue by using robot action. In this work, they use the robot to lift up the cloth before the reconstruction, which can significantly reduce the amount of occlusion and the set of possible poses. However, one of the drawbacks of the system is that the cloth manipulation process is open loop and cannot receive visual feedback. This is because the state estimation system can only be used when the cloth is being lifted in the air. So in this work, we propose to reconstruct the crumpled cloth from arbitrary configurations without lifting up the cloth. To do so, we marry a neural network with a self-supervised test and fine-tuning procedure. The neural network is trained with offline data to provide an initial estimate of the cloth. And then we used self-supervised test and fine-tuning to refine this estimate in an online fashion. So given a neural network which produces an initial estimate of the reconstructed mesh, we propose to refine the mesh with 2 self-supervised losses. The first one is the unidirectional chamfer distance between the mesh and the partial point cloud. We use the unidirectional chamfer distance instead of the more commonly used bidirectional one because we only have the partial point cloud from the visible surface. This loss will help align the prediction with the observation. And the second loss we deploy is called mapping consistency loss. Our deep reconstruction model is built of garment nets, which reconstruct the cloth by 3 steps. For each point on the 3D observation, we first map it from observation space to canonical space. Then we complete the shape in the canonical space and map it back to the observation space. By tracking each point throughout this procedure, we're designed to enforce a consistency between these two-way mapping. Both losses are optimized by gradient descent. We evaluate our method on two cloth manipulation tasks in simulation. The first one is cloth flattening, whose goal is to maximize the coverage of a crumpled cloth. Although this objective works well for cloths with simple structure such as towel, it creates undesirable results for cloths with more complex structure, such as shirts with opening. Therefore, we propose a new task called cloth canonicalization, whose goal is to transform a crumpled cloth to a predefined canonical pose. To conduct cloth manipulation, we put our perception model into a model-based framework that plans on the predictive mesh with a learned graph dynamics model, which can generalize to multiple tasks and different types of clothing. We compare our methods with prior works that doesn't explicitly reason about occlusion, such as VSF and VCD, as well as baselines that don't do test and fine-tuning. Our approach achieves the best results among all. All the methods are evaluated on both tags and averaged across 5 categories of clothing. Here is an example of how does the self-supervised test and fine-tuning incrementally improve the quality of the mesh. And we also deploy our model for physical experiments, and we show that it works well for cloth flattening. So in summary, our method estimates the full cloth structures from arbitrary crumple configuration by using a combination of a neural network and a test and fine-tuning procedure. When integrated with a learned dynamics model for planning, it achieves the state-of-the-art results for cloth manipulation. Please feel free to come to our poster if you have any question. Thanks for listening.
Thank you. We will now have a short Q&A. Please come up to the microphones to ask your questions, and we invite all of the speakers up to the stage as well. While people are thinking about questions, I'll ask the first one. For equivariant transporter networks, I was curious whether constraining the network to be equivariant reduces its expressivity in any way.
Sorry, could you repeat your question?
Yes, my question was whether constraining the network to be equivariant reduces its expressivity at all.
Yeah, so I think one constraint here is that you might limit the type of task that we could be solving. For example, if you want to always place one object to the bottom of the table, then the task itself doesn't really have the equivariant property that we are encoding. So yeah, I think that's one kind of limitation in the expressiveness. I think in order to make it work, all of the tasks that we are looking at must have the defined equivariant property that we have in our network. That's a great question, by the way. Thank you.
Great, thanks. Looks like there's a question on the left mic.
Yes, thank you. I have a question for the play it by ear paper. So I'm curious to what degree you think the audio part of the system is picking up on spectral features like frequency or just amplitude features, like just detecting whether a sound is present versus the quality of that sound. I'm just curious on your opinion there.
Yeah, sure. That's a great question. So we haven't done any official metrics, but I can give you an anecdote. So for the packing peanut versus screw task, from the spectrogram, they both have the sort of noise spike, but for the screws, we see little tiny harmonic little nodes on there, and so that's what it's picking up. Similar with the keys, the way it's jangling, it's more distinct. It's very distinct with the spectrogram information, so it is doing some sort of differentiation based on the spectral information. Hopefully that answers part of the question.
Yes, very cool. Thank you.
I also have a question about play it by ear. I think it's a very interesting topic inspired by human intuition. And I'm curious, if the robot has to explore, if the key is not right in the bottom of the robot hand, what kind of information actually resulted the action. So, for example, I'm curious what kind of exploration strategy the robot used to find the key if there's no any sound information because there's no key in the bottom of the robot hand.
For our version of the experiment, at least, I believe you're referring to the hard version. When the keys aren't, when there's no sound made directly on contact with the keys, we defaulted to a leftward searching motion first, and then if it made a sound, then it would proceed with the grasp. If no sound was made yet, we would also move to the right. So it's a left and a right searching motion.
Okay, thank you.
Great. I have a question for the RoboCraft paper. Since you removed the temporal correspondence, then that makes the dynamics model fairly unconstrained. Do you find that if you look at the motion of the particles in simulation, do they still actually move in the correct way on the individual particle level? Or is it more just that the global movement of all of the particles ends up being roughly correct?
Yeah, that's a great question. So we find like, although there's no temporal correspondence, using transfer distance and Earth mover distance can still achieve very accurate movement, both in the particle-wise and also the global-wise. So, yeah.
Great, thanks. Question for the surprising effectiveness paper. How might you extend this method to be goal conditioned?
That's a good question. So I think if you want to condition the policy on the goal as well, that has to be somehow part of like the nearest neighbor matching, right? So in addition to matching on the goal itself, you'd have to match your current state. So I think you have to go like you had to be doing nearest neighbor matching on 2 inputs. Yeah.
Great answer. Sorry, do you have a question? Go ahead.
Sorry, I have a follow-up on the surprising effectiveness paper. Does the nearest neighbors matching phase of the system allow you to do some sort of out-of-distribution detection? So if the occlusions become large enough, could you detect that in the feature map? Is that an area of future work?
I mean, so I think that's an interesting question because we did see our model failed when we did like extensive visual modifications, and that's because like the nearest neighbor matchings were not good. So I think naturally the distances between like the distribution of the demonstrations we collect in representation space and those representations of those heavy modifications would be like out of distribution. So consequently, I think they would have like a high distance and not be able to be within the distribution to match well.
Okay, thank you.
One last question. Oh, is there a question? Yeah.
I have a question for the plate by ear paper. So in the bag identification task, did the proprioception include force torque sensing at the end effector? And if so, did you control for the weight of the bags to be able to tell whether it was using audio or not?
Could you repeat the question, sorry?
Yes, in the bag identification task, did the proprioception of the robot include force torque sensing at the end effector? And if so, how did you control for the different weights of the bag?
We only had X, Y, Z positions of the gripper for proprioception, and the weight of the bag wasn't that variable because it was just the same set of keys in the bag.
Okay. Unfortunately, I think we don't have more time for questions, but feel free to ask more questions at the poster. Let's thank all the speakers again. Great. The next talk, we have another block of 4 papers. The first of which is a learning-based iterative control framework for controlling robot arm with pneumatic artificial muscles, presented by Dieter.
Hello everyone, I'm Dieter Büchler, and I'm presenting the work a learning-based iterative control framework for a robot arm with pneumatic artificial muscles on behalf of Hauma, Bernhard Schückhoff, and Michael Mühlebach. The problem we want to tackle here is we want to play table tennis with this robot arm on the left. And this is difficult because we have to estimate the states of fast-moving objects and track fast desired trajectories. So the robot that we consider here has 4 degrees of freedom. each of which is driven by 2 pneumatic artificial muscles, which enable safe exploration of fast motions. The problems with these muscles is that they are highly nonlinear, and we have a lot of friction in the tandem drive. To get a better understanding of the system, we first identify a linear model in frequency space and revert it for the feed-forward control and use a PID control to have a first good controller. On the right, you see that the tracking performance is really bad. But on the left, you can also see what we learned from this experiment is that the nonlinearities that are visualized in the red curve on the left graph are significantly higher than the measurement noise depicted in yellow in the amplitude spectrum. So this means that the linear model is simply not enough to control the system well. To capture these remaining nonlinearities, we use a nonlinear convolutional neural network. And in addition, we want to generalize to arbitrary desired trajectories. For that, we need pairs of desired trajectories and the corresponding feed-forward controls. And we get them using iterative learning control. A quick reminder on iterative learning control. We first apply the feed-forward commands, observe the real outputs, estimate the disturbance using a Kalman filter, and optimize a squared optimal control problem to get the feed-forward commands of the next iteration. We also assume our linear model that we identified before with terms that capture the repeatable and non-repeatable disturbances. And by assuming this model, we also significantly reduce the number of iterations of each ILC execution. So here on the left, you see ILC in action, and on the right, you see the desired trajectories that we chose. You see the average tracking error achieved by ILC. And we also distinguish between training data and the validation data, where obviously the validation data set is not seen during the training of the convolutional neural network. So now we plug in our convolutional neural network. We chose a convolutional network because we wanted to capture the coherence in time, but also across the degrees of freedom. The input to this convolutional neural network is a window in time along the desired trajectory before and after the current time step, and the output is the feed-forward command of the current time step. So on the right, you see our approach with various amount of feedback. And on the left, in red, is depicted the performance that we achieve on each of these desired trajectories, where you see that on the validation data set, which is unseen, we achieve tracking performance in the range that also achieves ILC. And we assume ILC is the gold standard on this particular trajectories. So now we plug in our method and intercept real table tennis balls, and we almost intercept 100%. So to conclude, we learn a feed-forward part instead of feedback to avoid instabilities. We combine the well-known iterative learning control framework with deep learning to generalize to new trajectories and achieve excellent performance on a very challenging real-world and nonlinear task. Thank you very much.
Great. The next paper is iSDF, and that will be presented by Joe.
Hi, I'm Joe from Imperial College London, and I'll be presenting our work, iSDF, Real-Time Neural Sign Distance Fields of Robot Perception. In this work, we're tackling the problem of reconstructing sign distance fields in real time. We show the inputs here on the left, the depth and pose of a camera moving live in an environment. And on the right, we show the output, the reconstruction of the sign distance field. This reconstruction is produced by training a neural network in a continual learning manner. First, we're going to show some slices of the ground truth sign distance field for the environment. The sign distance field maps x, y, z coordinates to the distance to the closest surface to that point. Here we show positive values of the sign distance outside of objects in green and blue, and we show negative sign distances inside objects in purple and pink. Here we're visualizing level sets of the sign distance field. Note that the zero level set encodes the surface geometry of the environment. Sign distance fields are commonly used in robotics for navigation and manipulation for motion planning. The reason for this is that it's very easy to transform a sign distance field into a collision cost field simply by applying something like the hinge cost as shown there. Although truncated sign distance fields are commonly used in SLAM systems such as Connect Fusion, it's very challenging to reconstruct full non-truncated sign distance fields because simply applying depth fusion results in large errors away from surfaces. Other related work, such as DICP, tackles reconstructing objects using sign distance fields. However, these kind of works aren't real-time. In iSDF, we tackle the problem of reconstructing full sign distance fields for large scenes in real time. The most notable related prior work is VoxBlocks, which is a method based on voxel grids that reconstructs the sign distance field in a two-stage approach, first reconstructing the surface, and then doing an expensive wavefront propagation algorithm to compute the sign distances in all cells. In contrast, iSDF is quite different and operates by training a neural network in real time. This gives iSDF a number of positive properties compared to VoxBlocks. We'll show these by looking at the reconstructed surface for both of the methods side by side. The first key property is that iSDF is predictive. By this, we mean it could sensibly fill in partially observed regions, for example, completing the backside of this beanbag. Also, iSDF can denoise many noisy measurements, producing a smooth reconstruction of this wall. A second key property is that it's efficient. It can adaptively model different parts of the scene with different levels of detail, allowing it to reconstruct small objects such as this lamp accurately. It's also important to note that iSDF is only using 2 megabytes of memory here in the network weights, whereas VoxBlocks uses tens of megabytes to store the voxel grid. Here I'll briefly explain the supervision method we use to train iSDF. First of all, we select a bunch of keyframes from our keyframe set using active sampling. And then we backproject rays using random pixels within keyframes. The network is then queried at points sampled along these rays, and we compute a loss using a bound on the sign distance. The simplest bound we could use is the distance along the ray to the surface. However, this is a weak bound, and we instead choose to use the closest surface point in the batch to provide a bound. This is a much tighter bound and results in much stronger supervision for the network. We're now going to focus in on a single ray and look at how this bound is computed. Here we show the vectors going from each of the points along the ray to the closest surface point in the batch. These vectors can also be used to supervise the spatial gradient of the predicted sign distance. Lastly, we're going to show some qualitative reconstruction results for one ScanNet sequence and one replica CAD sequence. On the top on the left, we show the ground truth mesh, and below that, the reconstructed surface. On the right, we have two slices, a slice of the ground truth sign distance field, and below, a slice of the predicted sign distance field. We can see that the final reconstruction of the mesh is watertight and accurate geometrically. While the second reconstruction is playing, I want to highlight some other quantitative results that we found. We compared iSDF to both VoxBlocks and another method that runs on a GPU and is similar to Connect Fusion, and found that iSDF produces more accurate sign distance fields and also spatial gradient of the sign distance field, which is, of course, crucial for trajectory optimization. Lastly, we're also going to have a live demo running at the poster session later on, so if you're interested, I'd really encourage you to come by and check it out. Also, our code is open sourced, so if you do want to run this on your robot in your lab, I'd really encourage you to do so. Yeah, that's all for me, and looking forward to meeting people at the poster session later.
Great, thank you. The next paper will be POCD, presented by Joe and Veronica.
Hi, we're Veronica and Joe, graduate students at the University of Toronto, and we'd like to present our work on probabilistic object-level change detection and volumetric mapping in semi-static scenes. Nowadays, we're seeing a lot more robots being deployed in human-centric environments, like this warehouse robot moving equipment from one side of the facility to the other. However, long-term autonomous operation is still a big challenge, and a key issue are semi-static objects that appear, disappear, and gradually move over time. Failing to properly update the map when the scene changes can lead to failed localization and lost robots. We aim to develop a system to track semi-static changes in the scene and output an up-to-date map with the current scene configuration. In this presentation, we'll talk about our probabilistic object-level mapping method to tackle exactly this challenge, and we evaluate our method on a real-world data set of a warehouse environment that we collected and released with this work.
Let's start by taking a look at the overview of our proposed system. Our system takes in RGBD frames, semantic labels, and camera poses as inputs. At each frame, our system extracts point clusters from the input data, and these clusters are associated with the mapped objects. While new objects are spawned, we also construct a iSDF volumetric model for each cluster. Then we compute the geometric error for each associated object observation pair by comparing their volumetric models. With the geometric error and the semantic label, we propagate an object-level state distribution to estimate the stationarity for each mapped object. And finally, we can construct the updated map just using the reliable objects from the map. So the core of our system is this object-level joint distribution. Imagine our robot encounters a pallet in the warehouse. The current model estimates an accumulated geometric change of 3 centimeters with an estimated stationarity of 90%. However, the current depth measurement indicates a geometric error of 2 centimeters with a predicted stationarity label of likely static. So now our system needs to estimate if the objects change or not. So to answer this question, we can apply Bayes' rule to iteratively update the object state based on new measurements and previous measurements. So inspired by previous work on stereo depth estimation, we parameterize the object state with a Gaussian beta distribution. The intuition is that we expect objects to stay around their original location in a semi-static scene, and the stationarity is just a probability between 0 and 1. So on the other hand, the measurement likelihood is decoupled as a product between semantic and geometric terms. The geometric error term is modeled as a Gaussian uniform mixture weighted by the stationarity, as we expect the geometric error to be a zero-mean Gaussian if the object did not move. If the objects change, then it could be anywhere. The semantic heuristic is modeled as a Bernoulli distribution, as we expect likely static objects, such as shells, will have a high chance of staying around. So putting everything together and apply moment matching, we can derive an approximate solution for the posterior. So on the left, we can see that under consistent measurements, both the object state, confidence, and stationarity increase. And under inconsistent measurements, on the scene on the right, we see a huge drop in stationarity. So we evaluate our system on a robot in a warehouse. As in the top row, our system constructs a volumetric object-aware map from scratch when first deployed. And after scene changes in the bottom row, our system discards the changed objects when sufficient observations are made.
To see our Bayesian model in action, we look at the evolution of the state distribution of just one box in the scene. Now, before the scene changes, the measurements align very well with a stored model of the object, so the stationarity score goes to 1 after just visiting the box twice. After the scene changes, however, the robot detects a significant mismatch, the stationarity score drops below a threshold, and the box is wiped and reconstructed at its new location. We compare our work against 2 recent semi-static mapping methods, FAIRS, which does voxel-level updates, and Panoptic multi-TSDFs, which uses a heuristic to estimate stationarity. Our method outperforms the 2 in precision on our warehouse dataset, and the figures here show the final map produced on a sample trajectory. Now, our object-aware probabilistic method produces the least amount of false positives after a scene change, as highlighted in red, while maintaining a very high level of scene coverage, as shown in green. And in summary, we derived a Bayesian update rule to propagate object stationarity and pose change assessment using both geometric and semantic information. We introduce a novel online object-aware map maintenance framework leveraging this derived Bayesian update rule. And finally, we collect and release a real-world change detection dataset captured in a warehouse setting on a robot platform. Thank you very much for listening, and we'll see you at our poster session.
Thank you. The final paper of this session is DICP, presented by Hitesh.
Good morning, everyone. I'm Hitesh, and I'm here to present our work on Doppler iterative closest point algorithm. This is joint work done along with my co-authors Bruno and E at AWA. Existing variants of ICP that solely rely on geometric features usually tend to fail in featureless and environments with repetitive structures such as tunnels and highways, as seen on the video on the left here. Furthermore, the presence of any dynamic points tends to degrade the pose estimates from ICP. Here we see ICP registers the point set to the motion of the dynamic vehicles in front of us rather than the static wall. We first describe the basic principles of Doppler velocity measurement using FMCW LiDARs. We then present a new Doppler velocity error term for robust point cloud registration, a simple method to reject outlier points, and finally present some real-world results. So given the distance measurements from the FMCW LiDAR, we can compute the unit direction vectors to these points. Note that the sensor is moving with certain velocity, and assuming all these points are stationary, we would observe an equal and opposite relative velocity on these points. The Doppler velocity is basically the projection of these relative velocities along the radial direction of observation. Next, a quick primer on ICP. Given a source and a target point cloud, the iterative closest point algorithm seeks to first match correspondences between the two point sets and iteratively minimizes a geometric error, such as point-to-point or point-to-plane, to optimize the pose. The pose vector consists of a rotational and a translation component. We approximate the sensor velocities using these pose components as shown here, where delta t is the sampling interval between the two scans. Using the estimated sensor velocity, we now estimate the relative velocities for all the static points. And again, we have the range measurements from the sensor. And using the direction vectors to these points, we can now predict what the Doppler velocity would be for all these points. And we do this in each step of the ICP algorithm. We now formulate a new objective function that minimizes the error between the actual measured Doppler velocities and the predicted Doppler velocities. We do this to optimize the sensor pose again. So in Doppler ICP, we basically jointly optimize the sensor pose using a geometric objective and a Doppler velocity objective. And these objective functions are weighed by a parameter lambda. Next, we present a simple method to reject dynamic outlier points. Points that have a high level of disagreement between the predicted and the expected velocities are rejected based on a predetermined threshold delta V. We now present some results on real-world sequences. The plot below represents the relative translation error between the two scans. Notice how the error for the point-to-plane method shoots up as the ego vehicle enters the tunnel, whereas our method, Doppler ICP, is able to constrain this registration problem well and estimates the poses with low translation errors. We present another sequence with a couple of dynamic vehicles on a highway scene. Again, on the left, we see that the point-to-plane method aligns the point sets to the motion of the vehicles in front of us, whereas Doppler ICP registers the point set correctly to the static wall. The data for these sequences were collected using AWA's Ares-1 FMCW LiDAR. In summary, we present a new Doppler velocity error term that is independent of the geometric structure of the environment. The combined Doppler ICP objective not only achieves significantly lower registration errors, but we also observe that it helps the ICP algorithm converge faster in all other scenarios. We also presented a simple method to reject dynamic outlier points based on the expected Doppler velocity measurements. Do join us at the poster session later to know more. We implement Doppler ICP as part of the Open3D library, and the source code is available on our GitHub. Thank you.
Great. We will now have a short Q&A. Please come up to the microphones, and we invite all the speakers to come up to answer the questions. I'll start with a quick question for the first paper. I'm curious how does, which is a learning-based iterative control framework. I'm curious, how does the method handle large disturbances?
Yeah, so it is true that the disturbances need to be kind of limited. But the balls that we, for this particular task, were already quite different. So they were around 20 to 30 centimeters apart. So this kind of disturbances we can definitely handle. But there's no real principled way of actually answering this question. Yeah.
Yes, go ahead.
This question is for the iSDF paper. Do you know how we might model other attributes? Currently you do depth reconstruction, but if you needed texture, color, or other stuff, is there a way of doing this straightforward manner?
Yeah, it would be very straightforward to make the network multimodal. So yeah, currently it's just predicting a signed distance value, but you could easily add color. In fact, we did experiment with this, but kind of found it simpler to just stick with depth in this case. And yeah, you could trivially add color. Then you need to have some kind of render loss and training, or you could add other scene properties into the network by just adding multiple heads to the network to output these different properties.
Cool, thanks.
It's also for iSDF paper. Do you need a very accurate camera poses? If yes, how do you get the accurate camera poses?
Yeah, so in our experiments, we do assume that we know the poses. So we did some experiments in a synthetic data set when we had poses available, and we also used a ScanNet data set for the other ones, which also provides poses. Yeah, it would be quite simple to add some pose optimization into the system and kind of have some bundle adjustment going on instead of just the mapping. There's some choices about what loss you would use to refine the pose. We did experiment with just using the same loss that we're using to train the signed distance field to optimize the pose, but that didn't work super well. And so I think that some kind of loss based on a render of the depth would be a sensible way to do it. And we have looked into that, and that's something we're continuing to work on.
Okay, thank you.
Sorry, a question for iSDF. Do you think that method can be used for recognizing terrains and uneven surfaces?
Sorry, recognizing what?
Terrains, different uneven surfaces like rocks and stones, and I'm thinking of legged robots locomotion, basically.
Yeah, sure. I guess iSDF is reconstructing a 3D map, and so yeah, you can easily do things like extract the normals from the surface, or kind of convert that into a mesh, and then you could do some kind of recognition based on the mesh. Or you could do some kind of semantic labeling. As I was saying, you could easily add heads to this network to have a multimodal predictions, and so you could add like a semantic head to this network, and in fact, that's been done in lots of related work before.
Thank you.
I'm actually another question for iSDF. Yeah, sorry. I was wondering, the network, is it pre-trained at all? And if it isn't, how do you think it's completing the backsides of objects? What biases is it able to learn to do that?
Yeah, it's a good question. So it's trained completely from scratch. We randomly initialize the network at the start of each run. Obviously, this isn't the optimal thing to do because we have no prior information about the scene. But yeah, so the way it can complete the backside of objects is that, yeah, so when it's reconstructing the parts of the scene that it can see, it's learning some kind of feature set that is kind of used to reconstruct, and then it's kind of repeating these features in the unobserved regions to sensibly fill in like a self-supervised way.
Thank you.
Great. I think that's all we have time for now, but feel free to ask more questions at the poster session. Let's thank the speakers one more time.